So, remember last time I mentioned that, or really the main point was that given any real number alpha, there's a continued fraction representation of that real number. So alpha has a continued fraction, a0, a1, a2, etc. It's a continued fraction with the ai's all integers. So it's a simple continued fraction. And it goes on forever if and only if alpha is not a rational number. So this is infinite. That's equivalent to alpha not being in the rationals. So every real number has such a representation. That is, alpha is equal to a0 plus 1 over a1 plus 1 over a2 plus da da da. Where, again, the meaning of this is you truncate at some point, you get a rational number, and you keep truncating, and you get rational numbers that are closer and closer together, and you take the limit of that sequence, and it's equal to alpha. And the way you construct the a sub i's is very straightforward. You take the floor, you basically just write alpha equal a0 plus t0, where 0 less than t0 less than 1. Then you invert t0 and write that as a1 plus t1, and you just repeat this process. And a bunch of integers pop out, and the integers right here are the continued fraction expansion of your number. Okay? So, in the situation of rational numbers, when you take, or in the situation of decimal expansions, if you take a number, then it has a decimal expansion, and that expansion repeats if only if the original number is rational. So you'll have a decimal expansion that eventually is repeating. Maybe it's all zeros, but maybe you have a repeating pattern like 0.333333. And that happens if and only if the number is rational. So you might ask, what's the analog of that here? So here's the theorem. A continued fraction is eventually periodic which means, so i.e. it's of the form a0, a1, am, say am plus 1, an, and then this part right here just keeps repeating over and over again. So it could start out however you want, and then suddenly it just keeps repeating the same thing over and over again. Exactly the same thing. Not like some nice pattern, but the exact same thing repeatedly. So an example of one of these is the continued fraction where it's just 1 repeated over and over again, and that's the continued fraction of the golden ratio. Use numerators and so with the property that the numerators and denominators of the partial quotients are Fibonacci numbers, which is kind of funny. So here's the theorem. It's eventually periodic, if and only if. So let's write as alpha. If and only if alpha is a quadratic irrational. Which is a, I think, old-fashioned sounding adjective, quadratic irrational, or description of something. And what it means is that, i.e., alpha is the root of a polynomial that's quadratic, so with integer coefficients. So alpha is a root of some quadratic polynomial ax squared plus bx plus c with a, b, and c integers. And alpha is not in Q. So that's what a quadratic irrational is. It's an irrational number that's quadratic. Irrational meaning it's not a rational number, and quadratic meaning it's a root of a quadratic polynomial. Which, of course, by the quadratic formula, you can always write as, some rational number plus a square root times a rational number. The square root of an integer times a rational number. All right, so this theorem is actually pretty hard to prove. It takes 2 whole pages in my book, and one of the pages is really, really technical. It would at least take an hour to carefully go through, and it's kind of a clever argument. I'm going to prove the easy direction right now, since that'll only take a few minutes and it's really pretty easy. So one direction here is hard and one direction is easy. So the easy direction is, if the continued fraction is eventually periodic, then the number that it represents, the limit, is a quadratic irrational. That's going to be really easy. So this direction, eventually periodic, implies it's a quadratic irrational. The other direction is much trickier. So we're just going to prove this one, not the other one. See. Okay, so our continued fraction looks like a0, a1, a. I don't want to use the exact notation I use in my book because it's kind of clean. We're writing this instead of that kind of messy thing there. Plus 1 plus h. So an and then an plus 1, an plus 2, or an plus h. Repeating. Okay? So it's just something that repeats over and over again. So let's try to prove that the limit of the value of this continued fraction is a quadratic irrational. Okay? So here's how we're going to do that. So we'll just focus on this part for a minute, and well, let's see. Actually, we could just do it directly. So here's what we'll do. Notice that this is exactly the same. So this is an infinite continued fraction. It's this thing repeated over and over again. Let's just think very carefully about this for a moment. We'll see that this is exactly the same as the finite continued fraction is 0, a1 up through an, and then the very last real number in this continued fraction, which no longer has integer partial quotients, is literally the value of the repeating part at the end. Okay? So notice what I've done is I've said this infinite continued fraction, which is these n plus 1 terms at the beginning plus these h terms repeating over and over again, is equal to and everything here are integers. These are all integers. Down here, I've written down a continued fraction with exactly n plus 2 terms in it, and the last term is a real number. Some, real number is not an integer, and then the other ones are all integers. Okay, so this is one element of R. Okay, does that make sense? The statement, and now this I think follows immediately from some lemma I've mentioned before, but just in case, just to make it clear to you, let's just imagine, just to go back to the definition, writing out each of these, just so you can see that they're obviously the same number. Okay? I'm just going to do that, kind of drawing this out a little more, but it will make it easier to understand. Unless nobody wants me to do that. I think you didn't want me to, so this one looks like there's a0 plus 1 over a1 plus dot dot dot, all the way down the line, plus 1 over an plus 1 over an plus 1 plus 1 over an plus 2 plus dot dot dot. This one looks like everything up to here is exactly the same, but then suddenly you have one more term, so that one more term is what you would put here, but that's exactly this continued fraction that we have here. Okay, so it's just this is really just a trivial statement from the definition of this notation. Okay, and now we're going to use the only thing we ever use, which is that that sequence of numbers Pn and Qn. Okay, every single thing we ever prove, it's basically we just use them. So this is a continued fraction, and so it's equal to Pn plus 1 over Qn plus 1 for this continued fraction, where the P's and Q's are given by that recurrence. So let's write out what they are. Pn plus 1 is the n plus first thing here. So it's this thing at an plus 1, comma, an plus 2, up to an plus h. Repeating. That's the last one times Pn plus Pn minus 1. So this is that Fibonacci looking thing. Divided by, now it's exactly the same thing, but for Q. Times Qn plus Qn minus 1. Okay? So I've used the thing that simplifies all the algebra which we proved on the first day when we started talking about continued fractions. Now the nice thing is that the Pn and Qn for the subscript up to n, they're just the Pn and Qn for this continued fraction at the top, because the two are exactly the same at the beginning. And so these are integers. Pn, Pn minus 1, Qn and Qn minus 1, these are all integers. Because they're defined by some recurrence, each one is just the partial quotient of the continued fraction times that thing plus the previous one. So these are all integers. This quotient is alpha. The thing we're interested in is the limit of this sequence. And that's what oh, look, this is also, oh, sorry, what do I do? So what do we have? It's tempting to look at minutes, and I will. See, so this is hard because we have all this stuff at the beginning, and it's annoying. So imagine, what if all this stuff at the beginning were gone? Then this alpha would be equal to this thing at the top, right? And in fact, in my notes, what I do is this proof in 2 steps. First, I just forget about everything at the beginning, pretending that there's nothing there at all, and then prove it. We show that the thing is a quadratic irrational. And then once you've done that, it's actually really easy to get the stuff at the beginning, because all you do is just change it by some integers. You're just like doing some integer arithmetic. So actually, let's change the argument as follows. So this is all true, but it's much easier to deal with if only this were alpha as well, and we can get that by just proving something slightly different first, and then we'll use that. So let's let, say, beta equal an plus 1 through an plus h, repeating. It's weird, but it is the argument. Yep. Okay, so, yeah, this is pretty cool. So, we have beta, let's just let it be this, and let's just try to deal with this one first. And now here's the trick. So yeah, it's kind of surprising. So what you do is you write it as, oh, that's cool. Okay, a0 through an plus 1 through an plus h. Except this would just be, sorry, this should just be actually, it's so confusing to explain this. This is right. Okay, an plus 1 through plus h. Oh, okay. So all I've done is taken this one thing with h things repeating and just put the first h things at the beginning and then put the rest there. Okay? So I'm just going to change everything so that in this argument, I would end up with an alpha here and also alphas here and here. And once we get that, we'll be able to use that result to get what we originally were interested in. So it's just like 2 steps. So just let beta be the value of this continued fraction. Now, a little trick is just use that. If it's this thing repeated over and over again, just take the first part of it and do that. Now let's do exactly the calculation we did before. So you get that this is equal to, so this beta is equal to that quotient, which is the repeating part, an plus 1 through an plus h bar times pn plus pn minus 1. Though I guess technically the subscript there should really be, since there's h of these and you start at 0, it should really be h minus 1 and h minus 2. But they're still integers, that's all that matters. An plus 1 through an plus h bar times qh minus 1 plus qh minus 2. Okay, so it's exactly the same as what's over here, except a0 through an are, I'm just going to do the special case when they're equal to an plus 1 through an plus h. Okay? It's a trick, and it's going to work. Because look, this is beta, and that's beta as well. So this is beta times an integer divided by, plus something, divided by beta times some other integer plus something else. And so now you have a quadratic relationship over the integers that beta satisfies. So beta is a root of a quadratic polynomial. And it can't be a rational number because if you consider the continued fraction of a rational number, it terminates at some point, whereas this one doesn't terminate. So this implies that just multiplying both sides through, that beta squared times qh minus 1 plus beta qh minus 2 minus beta p sub h minus 1 minus p sub h minus 2 is equal to 0. So beta is a quadratic irrational. However, that beta is the thing right here. So we just proved that this continued fraction converges to something that is a quadratic irrational. But on the other hand, the original continued fraction is an integer plus 1 over an integer plus 1 over an integer, all the way down to 1 over a quadratic irrational. So if you just think about simplifying this, you'll end up with a quadratic irrational. That might not be obvious to some people, because you might have to remember that you can rationalize the denominator. So remember when you were in, I don't know, junior high, and you had something like 1 plus square root of 3, or sorry, 1 over 1 plus square root of 3. And you're like, oh no, there's a square root in the denominator. What did you do? You multiplied the top and bottom by something clever, namely 1 minus root 3 over 1 minus root 3, like that. And that gave you 1 minus root 3, and it got rid of these square roots in the bottom. So you got 1 minus plus root 3 minus 3, so you get minus 2. So anytime ever when you're taking, if you take 1 divided by a root of a quadratic polynomial, then by rationalizing the denominator, you can always make it of the form something plus something times the square root. And so you just keep repeating that here. Every time you have 1 over this thing involving square roots, you can always rationalize the denominator as you go, and the result will be expressible in terms of that single square root again. And so the original thing has to be a quadratic irrational. So that's the easy direction. Notice, I mean, all this is a slight generalization of how we computed that the golden ratio is equal to the value of the continued fraction 1 plus 1 over 1 plus 1 over 1 plus 1 over 1. It's exactly the same thing, where you see the pattern, the thing that starts repeating, you make it a variable, then you find some quadratic relationship that satisfies. Okay? Any questions? And this is pretty much where things stop being clean and simple. There is, of course, a pattern in the continued fractions of the powers of e, which I showed you before. But if you look at things like the cube root of 2, trying to understand the continued fraction of this not very much more complicated number, it just looks sort of, it's really hard to understand. There's no simple formula for it as far as we know. And there's a lot of basic questions about it that aren't clear. I think you expect that arbitrarily large partial quotients appear. Definitely you'd expect that, but you don't know how to prove it. Okay, so the next thing I'm going to do is discuss what happens when you consider continued fractions of just very general numbers, not necessarily quadratic irrationals or rational numbers, and what they look like. And I'll do that using the computer.